Let's get started. So last time we finished up, with me stating that RIP implies JL. We already know that JL implies RIP just by union bound over, well, basically because RIP is just a subspace embedding for n choose k different subspaces. So union bound over a subspace embedding that works with high probability. But there's the other direction by Krahmer-Ward that says, say you have an epsilon k RIP matrix, and you take this diagonal matrix with signs in the diagonal, so sigma i's are independent random signs. Then pi d sigma, basically take pi and randomly flip the sign of each column, satisfies distributional JL, where the epsilon is the same as the old epsilon up to a constant, as the RIP epsilon, and the failure probability is exponentially small in k, the sparsity that you satisfy RIP to. And so there's a reminder of what distributional JL means. It means that you preserve any fixed unit vector with high probability. So we're going to prove that today. And I started off the proof last time, but now we're going to finish it. So I have a key trick that's used repeatedly. There are kind of two key tricks used repeatedly in this proof. One is that if you apply d sigma, so in general, this d, think of d as like an operator. If you give it a vector, it's just the diagonal matrix that has that vector on the diagonal. So if you look at d sigma x, it's just equal to dx sigma. Okay, so that's which means that we can write this L2 norm squared as a quadratic form in sigma. And then we want to say that this quadratic form in sigma is concentrated about 1, is about the L2 norm squared of x. Okay, so we have tools for that, namely Hansen-Wright. Okay, so we're gonna do that. So I can write x. Let me partition the entries of x as follows. Okay, yeah, question?
So just clarify the notation. So dx sigma is just like changing diagonal to x and then sigma to a vector.
Yeah, sigma is, yeah, exactly.
Okay.
Yeah, sigma is that vector. Okay, so first of all, what I want to do is I want to just sort the entries of x by magnitude. This just amounts to permuting entries of x, which is the same as permuting columns in pi. So just do that. It doesn't change any norms of anything. I'm sorry?
Oh, that's x the vector.
Yeah, x the vector we're trying to preserve. So I'm going to assume that the entries of x are sorted. And also, x paren I is going to, for me, denote a k-sparse vector, which is the entries of x that correspond to the ith block. Okay, right? So block one is x1 up to xk. Block 2 is xk plus 1 up to x2k, etc. So xi is the k-sparse vector corresponding to the ith block in the sorted order. And then also pi I is the k columns of pi from the ith block. So pi 1 would just have the first k columns, etc. Okay, so I want to now write down this matrix x. X is just dx pi transpose pi d, just from that. And I want to partition the entries of x into different pieces. Okay, so there are 4 pieces. There's the diagonal blocks, right? So each one of these, by the way, looks like, you can imagine taking this n by n matrix, x is an n by n matrix, and just breaking it up into k by k blocks. Right? So imagine this thing's actually a bunch of k by k blocks. So that there'll be n over k blocks and n over k blocks. Okay. And I'm partitioning those blocks. All the diagonal blocks I'm going to call a matrix A. Okay? So A is just the diagonal blocks and everything else is zeroed out. Then this is B. Okay? So B is actually a matrix which just has this and everything else is 0. And then, of course, this is B transpose. And then C is everything else. So C is everything that's not in the first row, not in the first column, and it's not in the diagonal block. Okay, and then we're going to break up X like this.
Why are the diagonal blocks all the same?
Oh, I didn't mean to imply that they're all the same. Oh. What I meant to say was A includes those. So A, if you draw out A, it looks like it has stuff on the diagonal blocks, and then everything else got zeroed out. That's what I meant to say. right? So in particular, if you look at, the ith block of A, so if you look at, for example, AII, this is equal to dxi pi I transpose pi I dxi, right? And similarly, you can write, and also, Aij is 0 for I not equal to j. Okay. And you can write similar things for B and C, et cetera. So what we're going to show with probability 1 minus 2 to the minus c prime k, we'll have a few things happening. We'll have that sigma transpose A sigma will be 1 plus or minus epsilon. And then we'll have sigma transpose B sigma, sigma transpose B transpose sigma, and sigma transpose C sigma. So all these guys will be like at most, O of epsilon. Right. So that's what we're going to show now. Okay, so let's do this. So first of all, sigma transpose A sigma is, what did we say A was? It's that. So it's the sum over all I from 1 to n over k of sigma transpose dxi pi I transpose pi I dxi sigma. Okay. And actually now, like only the columns in the ith block even matter here. But again, just basically, let's just, for this part, we're just going to undo the trick we just did. So this is the same thing as sum over I xi transpose d sigma I pi I transpose pi I d sigma I xi, which is the same thing as sum over I pi I d sigma I xi L2 norm squared, right? But now, remember, d sigma I xi is a k-sparse vector. We broke it up into these blocks of size k, so pi preserves it. So this is equal to 1 plus or minus epsilon times sum over I d sigma I xi L2 norm squared. What does d do to x? It just changes signs in entries of x. It doesn't change the norm. So this is the same thing as 1 plus or minus epsilon sum over I xi squared, which is just the same thing as x squared, which we said was 1. Okay, so that's that. That's simple. Oops. Okay, so now let's deal with these other things. Okay, so I'll just tell you what the game plan is. So sigma transpose B sigma. If you look at this picture, well, let's write what that is. Okay, so B. Notice that B now is the same thing as d x1 pi 1 transpose pi minus 1 dx minus 1. Okay, what do I mean? What do I mean by minus 1? I mean x minus 1 is basically the vector x2, x3, x n over k. So it's the vector you get by deleting the first block. So by minus 1, I just mean the vector without the first block. Okay. Good. So so now what we have is questions? Is this clear? Right? B is the part. B is this thing that's missing this piece right here. So sigma transpose B sigma is now sigma. Whoops, this should be a 1. Okay. 1, 1, minus 1, minus 1. Right? So this, yeah, 1, 1, 1, 1, 1, minus 1, minus 1. So it's a k by n minus k matrix. Okay, you can, in actuality, as I've described it here, all these matrices are n by n. Okay, but kind of the first, like all of this whole part is, well, in B, kind of this whole part is 0. So kind of all the action happens with this k by n over n minus k part of it. So let's just pretend that it's actually k by n minus k. So sigma transpose B sigma now becomes sigma 1 dx1 pi 1 transpose pi minus 1 dx minus 1 sigma minus 1, right? And the thing to note here is, I mean, where's the randomness, right? The randomness is in sigma. The thing to note here is if you look at this versus this, these are independent of each other, right? Because this is the first k entries of sigma, and these are the last n minus k. Okay? So what we're going to do is we're going to say, look, if you look at kind of this whole thing, without that part, just look at this. This is a vector. Okay? And what we're going to argue is that this vector, because pi has RIP, this vector will have small L2 norm. Okay? And then now what do we have? We have some vector v transpose sigma. When we've seen that before, right? If you take a dot product of a fixed vector with a random sign thing, you'll get a good tail bound. That's Kinchin. So that's what we're going to say. We're going to say, just like, forget about the fact this is random. Actually, this won't even involve randomness. Just with probability 1, this vector here will have small L2 norm. Therefore, by Kinchin, if you dot this product with this piece of randomness here, which is independent of this, then you'll get a good tail bound. Okay, so that's how we're going to handle B, and B transpose is basically the same thing. And then we're going to handle C by Hansen-Wright. Okay, just telling you where we're going. So claim. So let me call this vector V. Okay. Right. Yep. I think we'll get something like that. Yeah. So let's prove this. So the key part, I mean, notice that the L2 norm of any vector is just equal to the sup over y having L2 norm 1 of v dot y. Right? So let's look at this thing. v dot y is equal to sigma minus sigma 1 dx1 pi 1 transpose pi minus 1 dx minus 1 y minus 1. Okay. Good. Let me make sure I. So this is equal to now the sum j bigger than 1 of sigma 1 dx1 pi 1 transpose pi j dxj yj. Okay. I'm going to do the trick again where I say that this is the sum of j bigger than 1 of now x1 d sigma 1 yada yada. But this will actually be dxj. And this is at most now the sum j bigger than 1 of the norm of x1 times the norm of d sigma 1, the operator norm, times the norm of pi 1 transpose pi j actually, let me just be, so let's say that I think for this I'll actually need 2k RAP. It's not a big deal. Times the operator norm of dxj times the L2 norm of yj. Okay, good. Now, a couple things I want to observe. First of all, what's the one trivial bound is? Well, the L2 norm of x is 1, so the L2 norm of the first block is at most 1. So we'll just basically ignore this. Okay. If you have a diagonal matrix, what's the operator norm? It's the largest magnitude of any diagonal entry. But this is a sign. This is a sign on the diagonal, random signs on the diagonal. So this is also equal to 1. Now, what is the operator norm of this matrix? So in general, if you have a matrix M, the operator norm is the sup over all z of unit norm, z transpose m z. In general, it's the sup over all z prime of unit norm of z transpose mz prime. Right? So notice that the operator norm of pi 1 transpose pi j is just the sup over z prime of unit norm of pi 1 z pi j z prime. Right? That's the definition of the operator norm. But this is exactly something that we bounded last time. Remember we had a lemma last time, which was if you have two vectors that are each k-sparse but have disjoint support, and you hit them with an RAP matrix, right? The dot product will be O of epsilon, as long as it's a 2k RAP matrix, right? This is just because pi is 2k RAP, right? So in particular, it preserves the L2 squared of z plus z prime, and it also preserves z minus z prime. But if you sum the squared norms of those two different vectors, you get exactly or subtract them, you get something like 4 times the dot product, right, by parallelogram rule. And the actual dot product between these two vectors is 0 because they have disjoint support. Z only has support in the first block. Z prime only has support in the jth block, right? You have a question?
I'm missing something.
Yeah.
Why is Z and Z prime k-sparse?
So we're only looking at the jth block of pi being applied to z prime, right? So z prime is just a k-sparse vector, of course, with entries in that block. Yeah. So z and z prime are k-sparse. So by our lemma from last time, this thing is, O of epsilon. Right. So the operator norm of this thing is O of epsilon. Okay. This thing we'll deal with that soon. What's the operator norm of xj, of dxj? I mean, you don't give me a bound. Just tell me what it is. Equality. What is it?
X1.
X1? I don't want an upper bound. I just want an exact expression for this thing.
The max of the entries of X in that block.
Yeah, it's the L infinity norm of xj, right? It's, again, a diagonal matrix. So the largest eigenvalue is the largest magnitude of any entry on the diagonal. So, so let's do that. So this thing here, okay, is at most sum j bigger than 1 of O of epsilon times xj infinity times y L2 norm, or yj L2 norm. Right? Okay, but now here's again a trick that's called shelling. It's very common in some compressed sensing proofs. Notice that everyone in the jth block is smaller than everyone in the j minus first block. Okay, that's how we define these things. So this guy here is actually at most, well, let me put it like this. Yeah, it's at most, look at xj minus 1. So it's at most the largest guy in the previous block. So it's at most the average of the guys in the previous block. Right? And then by Cauchy-Schwarz, L1 norm is at most root k times the L2 norm. So this is at most xj minus 1 times root k, or over root k, by Cauchy-Schwarz. So this thing here is at most sum j bigger than 1. There's an O of epsilon over root k now. Xj minus 1 L2 norm times yj L2 norm. Okay. Question?
Norm on the right there, wait a second. And the term to the right, that was?
Cauchy-Schwarz.
Oh.
Yeah, sorry. Okay. So this trick is called shelling. Okay, where you kind of break up the vector into blocks after you sort coordinates by magnitude, and then you bound norms in one block by some norm in the previous block. So it's a very common thing in lots of these proofs, lots of compressed sensing proofs. So now what we do is we just finish off with AMGM. Okay, so this is at most O of epsilon over 2 root k, sum j bigger than 1 of xj minus 1 L2 norm squared plus yj L2 norm squared. But this is exactly, yeah. So this is exact, if you sum over j of this thing, this is at most the L2 norm squared of x, which is 1. And the same thing about y, you get the L2 norm squared of y, okay, which is also 1. So this is now, this whole sum is at most 2. So this thing is O of epsilon over root k. Okay. More, well, actually, I'm not sure what, maybe, I think these are Turing machines. Well, these are tapes for a Turing machine, given what the last class is. Okay, so good. So now going back to sigma transpose B sigma, the probability that sigma transpose B sigma is greater than epsilon, or some constant times epsilon. Well, that's equal to the probability over now sigma minus 1 that V transpose sigma is greater than C epsilon. But by Khinchin, we know this is Khinchin. This is at most something like e to the minus some constant epsilon squared over the square root of V, which we said is k over epsilon squared. So this is okay. Make sense? So now the only thing left is this guy. Okay. Yeah.
So let's just using the moment bounds of Khinchin and move into the bound.
Sorry, say it again. Yeah. So Khinchin says that all the p norms are at most the L2 of V times root p.
So we have root k and cancel it out. So we have the omega k.
Sorry? What is the question?
So basically, we just use the moment bound and then apply it. Use the PK1. Get that.
Wait. So yeah. So okay. So Khinchin says that for all p bigger than or equal to 1, V transpose sigma p is at most basically root p times the L2 over V. But yeah, so sorry. Sometimes I just interchange moment and tail bounds like this because we know they're the same. So this is exactly the same thing as this statement. Okay. So now all that's left is handling C. So let's do that. I'm going to erase the statement because I think we know what we're trying to prove. We're just trying to prove now that sigma transpose C sigma is less than epsilon, or some constant times epsilon. So Hansen-Wright well, it gives us concentration around the expectation. But sigma transpose C sigma, C has no diagonals, right? I removed everything on the diagonal blocks. So the expectation of sigma transpose C sigma is 0. So the probability that sigma transpose C sigma is greater than some lambda, where for less lambda is like C epsilon, is at most e to the minus some constant lambda squared over the Frobenius norm squared plus e to the minus some constant lambda over the operator norm. That's what Hansen-Wright says, right? So we just need to bound these two quantities, Frobenius norm and operator norm. Okay, so let's do that. So let's do Frobenius norm squared first. So this is equal to the sum over I, j both bigger than 1 of I not equal to j. So blocks, so I and j are block IDs. So they're not diagonal blocks, and they're not part of that top row of blocks or bottom or leftmost column of blocks of dxi pi I transpose pi j dxj Frobenius norm squared. Okay. And now what I'm going to do is I'm going to use the fact that, so I'm going to write an equality. So sum over all ij bigger than 1, I not equal to j of operator norm of dxi times operator norm of pi I transpose pi j times Frobenius norm of this guy. And this is just using the fact that, in general, if you look at the Frobenius norm of AB, it's at most the operator norm of A times the Frobenius norm of B. This is just an inequality that's true. Okay. I'll leave that as an exercise. I think we are OK to, I'll now erase that. I think we're OK to erase that. So this is just a general fact. And I think maybe you know where this is going. We're basically going to do the same kind of trick as last time. So that's now at most. So remember, pi I transpose pi j has operator norm epsilon, O of epsilon, and it's getting squared. So there's an O of epsilon squared. And then we have sum over ij bigger than 1, I not equal to j. That's the L infinity norm of xi. And then that's, well, the Frobenius squared, oh, and it's squared. Okay, that's the Frobenius squared of that thingy, but that's the diagonal matrix with xj on the diagonals. So that's just equal to xj L2 norm squared. Okay, and then we're going to shell. So this is at most O of epsilon squared times sum of ij bigger than 1, I not equal to j. Of this is at most, remember over there, this is at most epsilon over root k without the square. It's at most epsilon over root k times the, not epsilon. It's at most 1 over root k times the L2 norm of the previous block. And it got squared, so there's a division by k. And then now we have x I minus 1 L2 norm squared times x j L2 norm squared. And this thing here is just, at most, sum over I xi squared squared. But this thing here is just x squared, which is 1. So overall, we have that this thing is O of epsilon squared over k. Okay, so the Frobenius norm squared of C is at most epsilon squared over k. So now we just have to deal with the operator norm. That's the last thing. Yeah. This thing? This inequality? So take this quantity and square it. Now what are you going to get? You're going to get the sum over all ij xi squared, xj squared, which contains all these terms. Like all of these summands appear in the expansion of the square of this. Yeah, there's a square here, yeah. So, and this thing is 1, right? So now let's look at the operator norm. C is a symmetric matrix, okay? So this is just equal to the sup of y having unit norm of y transpose cy. Okay? So let's bound this. So we have, I'm going to stop writing sup from now on. So just pretend y is the thing that actually achieves the sup. So this is equal to sum of ij bigger than 1, I not equal to j, yi dxi pi I transpose pi j dxj yj. Okay. And this thing is at most that same sum of the L2 norm of yi times the operator norm of this guy times pi I transpose pi j operator norm times that operator norm times this L2 norm. Okay. And you probably already see what's going on here. This is it's basically the same trick over and over again. So now this is x infinity, xi infinity norm. I'm going to shell. This is also xj infinity norm, which I'm going to shell. So this is at most sum over ij bigger than 1, I not equal to j, yi L2 norm times, and there's also, this is O of epsilon, right? This operator norm is O of epsilon. So there's an O of epsilon over k. The k is because I get a root k from shelling this and another root k from shelling that, times xi minus 1 L2 norm times xj minus 1 L2 norm times yj L2 norm. Okay. And now this is at most O of epsilon over k times a sum over all I bigger than 1 of yi L2 norm times xi minus 1 L2 norm squared, right? Because if you expand the square here, you'll get yi x minus 1, yj xj minus 1, which is exactly what you have here. So and this is even bigger because when you square this, you would get the diagonal terms, whereas here you don't have the diagonal terms. Same thing over there. And then now we do AMGM. This thing here is at most, or not that. This thing here is at most 1/2 yi L2 norm squared plus xi minus 1 L2 norm squared by AMGM. And then we're summing that over all I. So again, when you sum these over all I, you get the square number of y, which is 1. When you sum these over all I, you get the square number of x, which is 1. A question?
Yeah, where did you factor 1 over k from? Did you keep the...
So, oh yeah, good. So this is actually the L infinity norm of xi, and this is the L infinity norm of xj, right? But then I'm going to shell again. I know that the infinity norm of the ith block is at most 1 over root k times the L2 norm of the previous block. So I picked up 1 over root k twice, which gave me a 1 over k. Yeah, so this was by shelling. So shelling twice for both of those, once for each of those. So this thing here is, again, O of epsilon over k. Okay. And then now we're done, because what did we say? So both of those, so good. So I'm not going to write it. I'll just point. So Frobenius norm squared is epsilon squared over k. Okay. So, and lambda is also basically epsilon, right? Lambda is some constant times epsilon. So what we have over there is e to the minus epsilon squared over epsilon squared over k. So the epsilon squareds cancel, and k comes up to the numerator. So that first term becomes exponentially small in k. And similarly, the second term also, because the operator norm is epsilon over k. Lambda is basically epsilon, so it cancels the epsilon, and then you get a k again in the popping up in the numerator. Okay, so we're done. We've shown exactly what we wanted to show. Okay? Yeah?
Is there the reason that we separate case B and case C is because in case B is 1, so we can just show it before that, and then in case C we can just do a 2 show to get it.
Or you're saying maybe we don't need to deal with B separately?
Yeah.
Just include B in, I mean, so yeah, so what you're saying might actually work. I haven't tried to do it that way.
B has 1. You can just show 1. I think that might be.
B does not have the diagonal block, right?
Yeah.
It doesn't, right?
It does not.
Yeah, yeah. Yeah, you can't shell, that's true.
Yeah,
You can't shell because
yeah, because we won.
that's true. But in principle, I mean, I don't see why. I mean, we're trying to show that this quadratic form is at most epsilon with high probability. And even if you include B, your quadratic form does still have 0 diagonal.
Yeah.
So you could still try and say this quadratic form has bounded operator norm and bounded Frobenius norm, which might still be true. But you might have to deal with the block number 1 separately.
Yeah.
Which we did, but I mean, you might be able to, but when I say deal with it separately, I mean just do Hansen right, but in your when you bound the operator norm and Frobenius norm squared, kind of deal with that part separately.
Yeah.
Such a thing might work. I haven't tried that. Anyway, any other questions? Okay. So that's the end. Okay, so we've come to the endpoint of something in this class, which is something you pointed out, which is there were all these. Okay, so first of all, let me say something, which is why do I care about this theorem, right, that RIP implies JL? So I think I mentioned before that if you, for example, if you, for example, have pi, which is SHD, is RIP, right? Or not without the D. Okay? Just sampling rows from Fourier or Hadamard. This is RIP. I think I gave some references last time. So now what it's saying is if you attach the D, satisfies distributional JL. Okay? And also, when I say it's RIP, I mean, S is random, so it's RIP with good probability. So actually, the best ways of getting kind of fast JL, the most sophisticated ways of analyzing the fast JL approach are using this. Okay. Also, remember at some point we talked about if you have JL, JL implies this Gordon's theorem, right? Because you look at these different sequences of TRs, and you have to preserve them all at different scales. So there was something like, if you recall the proof, or if not, you can review it. There was something like log 1 over epsilon, log of 1 over epsilon, different scales that we needed JL at in the proof of that. Not log 1 over epsilon, but log of 1 over epsilon prime, where epsilon prime was something like epsilon over the mean width. Okay, so we need a JL log 1 over epsilon prime scales, where epsilon prime was something like some epsilon over the Gaussian mean width, or t is the set of vectors we wanted to preserve. T is some constant. Okay. So what you could do is you can have enough rows in S such that your RIP at all these different scales simultaneously with good probability by a union bound. Okay. Which means that you'll be DJL at all these scales just because of the theorem we just proved. Which means that you could prove Gordon's theorem starting off with like an RIP matrix like this one. So the number of rows, so like for example, implies SHD to preserve T can have G squared of T over epsilon squared times polylog rows. This extra polylog is coming from the fact that you need to satisfy RIP at all these different scales. Okay. And the number of rows you need for RIP is off by log factors. And actually, that was kind of the that paper that I presented that time in lecture. That was their motivation. They wanted to say that this matrix can have this many rows and preserve things. And kind of once you have RIP implies DJL, and DJL implies Gordon-like theorems, then you just combine them. Okay. So anyway, yeah. So Yakir asked about, there are all these different kind of primitives that we've talked about in class, or things that I've defined: RIP, DJL, JL, Gordon, subspace embedding, et cetera, approximate matrix multiplication. And as we saw, they're all connected. Once you have one, or JL moment property, once you have one, it implies a bunch of things for the other properties, right? There's like this web of connections. So and we're sort of done in the class now with that web. Okay, so the stuff we're going to look at in the next few lectures is not going to be like using things that you've seen and showing that they imply new things. We're going to actually use new objects. Okay, so what I'll do is I'll prepare like a PDF, maybe with like a drawing the web or something, showing you that what implies what. Okay, so.
Can we meditate for like a few minutes to celebrate the finish of JL?
Wait, are we actually on this JL? Wait, I think, yeah, we are. I think we're done. We're done in this. We're still okay. We're going to use it for one more thing this lecture, but we're not going to use it explicitly. We're going to use RIP.
Oh, cool.
But we're done kind of showing that this property of a matrix implies that it also has these other properties, et cetera. Okay, so we're done with random sign matrices. That's and we're done. Yeah. So okay. Okay. So rest of today. So last time, remember we looked at basis pursuit? We said that if you want this L2, L1 mixed guarantee, then you can solve a linear program, and then you'll recover a vector that has this good guarantee, right? Now, that's all nice in that it's polynomial time, right? We know there are algorithms that solve linear programs in polynomial time, ellipsoid algorithm, interior point algorithms, et cetera. But kind of in the cases we're looking at, n, the dimension, it's like polynomial in n time, where n is the dimension. And we're imagining that n is huge, right? Like you have this 1,000 by 1,000 pixelated image, a million pixels. I don't want to spend n cubed time or n to the fifth or whatever. So one question is there a faster recovery algorithm than actually solving the basis pursuit linear program? Okay, so faster L2, L1 recovery than basis pursuit. Okay, and in fact, there are such faster algorithms. Okay. Most of these algorithms are iterative, okay, meaning that they start off by saying my recovery is the 0 vector, which has terrible error. And then there's this iterative step that you keep doing that every time you go through an iteration, the error improves. Okay? And as we'll see, you can implement the iterations quickly. Okay? And we'll show that kind of it converges to small error quickly as well. There are actually several iterative algorithms that have this kind of good behavior. One is, for example, COSAMP by Needle and Trop. There's iterative hard thresholding, which is what we're going to cover today. There are several of these. Today, we're going to look at this iterative algorithm. Okay, which is due to Blumensath, or the analysis of this algorithm in this context for L2, L1 is due to Blumensath and Davies. And this is in 09. Let me write down the algorithm. And then we'll prove what it can do. So what's the algorithm given as input? It's given as input y, okay, as well as it knows pi, okay, and it's also given an iteration count t. That's all we need to know. And let me just put a comment in this code. I'm imagining that y is equal to pi x plus e, where e is some error. Okay? And I'll write down what the recovery guarantee will be soon. So first step is we're going to initialize x0 to be the 0 vector. And then what we're going to do is we're going to say for I goes from 1 to t, xi gets set to, I'll say what this means in a second, xi minus 1. Actually, let me write this. Okay. So this is the iterative algorithm. So it maintains these iterates xi. Initially, it guesses that xi is 0, which is not good. And then pretend there's no e. Pretend that y is just pi x. Okay. Introducing e is, well, it's going to be useful when we prove our theorem. But so I mean, you can also say this thing handles kind of error both before the measurement and after the measurement, right? So x is actually a k-sparse vector plus error. So there's some error before the measurement pi is applied. And then in addition, there's some error after the measurement is applied. And we'll see kind of what error guarantees we get. But the way to view this is, look, what is y? Y is pi x. So pi x minus pi xi, 'i' is pi times x minus xi. 'i'. 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 And now pi transpose pi, in a lot of these things, you should think of pi transpose pi as trying to be the identity matrix. So pretend pi transpose pi were the identity matrix. We would have x minus xi plus xi, which is just x. And hk is what they call the hard thresholding operator, which just keeps the largest k entries in magnitude. Okay, so hk of z is z restricted to the largest k entries in magnitude. So this is the whole algorithm. And the theorem is that if you look at, we want an L2, L1 kind of guarantee. If you look at x t minus x, xt minus x, L2 norm, is going to be at most up to a constant. Two to the minus t times hkx plus x minus xk x minus hk x L2 norm plus O of 1 over root k times x minus hk x L1 norm plus the norm of E. Okay? So initially, of course, your error is at least the L2 norm of the head. Well, it's actually the L2 norm of x itself. But right, so initially your error is the norm of the tail, is at most the norm of the tail plus the norm of the head, which is x itself. But as you do more and more iterations, the norm of the head plays less and less of a role. It gets like exponentially decreased at every step. So if you do enough steps, this term goes away. And then what you're left with is the 1 over root k times the L1 norm of the tail, which is what we're used to, plus the L2 norm of the error, plus the L2 norm of the tail. So this is something that doesn't look familiar from before, right? Before, we just had 1 over root k times the L1 norm. I claim, though, that this and this is basically bounded by that. Why? Because, I should say something about the conditions. If pi satisfies epsilon 3k RIP for epsilon has to be smaller than 1 over 4 root 2. Okay, so if epsilon is less than some fixed constant and it satisfies 3k RIP, then you get this guarantee. So imagine that actually k were 2k. So this had 6k RIP. Then what would this be? This would be the 2k tail of x, right? But we can bound the L2 norm of the 2k tail by basically this, by shelling. Okay. Why? Because if you look at if you look at the 2k tail, this is going from block 2 onwards, or block 3 onwards, sorry. Everything except the top 2k people, so going from block 3 onwards. But if you look at the L2 norm of the third block, it's at most the L2 norm of the second block, which is at most 1 over root k times the L1 norm of the second block. So you can shell, and you'll get 1 over root k times the L1 norm of the tail. So if you just double k, you can basically make this thing be this. So it's still giving us the kind of guarantee we're familiar with. Kind of the only new thing is this part, which is sort of unavoidable because you're starting off with some bad estimate. What are you going to do? But it exponentially decays. Okay, so questions about the statement of this theorem? Okay. So let's prove it. Before I prove it, I want to introduce some notation. So let xk denote hkx. So it's actually k-sparse. We'll assume x equals xk. So in reality, pi x is equal to pi kind of xk plus the tail. Well, let me write it like this. Pi x plus e up there is actually equal to pi xk plus the tail plus e. I'm gonna view this as being pi xk plus e tilde, where e tilde is e plus pi times the tail. Okay. So what we're gonna do is we're gonna show this theorem, but imagine that e is actually e tilde. But then when you bound the L2 norm of e tilde, you'll get that it's at most the L2 norm of e plus the L2 norm of this thing, and this turns out you can bound in terms of these anyway. So really, the interesting thing is understanding this. Let's pretend that's actually k-sparse. So set up the notation. So we have that y is now equal to pi xk plus e. We have that, let me define RT is equal to xk minus xt. So it's like the residual at time t. Let me also define AT plus 1 as being equal to basically that step before we apply the hard thresholding operator. So this is equal to xt plus pi transpose y minus xt, which implies that xt plus 1 is just the hard thresholding operator applied to AT plus 1. Yeah, sorry, there's a pi here. Okay, let me also say gamma k star is equal to the support of xk, which is subset of indices. And also gamma t is just the support of xt. And bt is equal to gamma k star union gamma t. Okay. So Right. So ultimately, I want to get a good handle on this, right? Which is the norm of the residual after t steps. So let's write that down. So we have that x minus xt plus 1, L2 norm, is equal to, well, this has support. These two vectors both have support in bt plus 1. So this is equal to x bt plus 1 minus xt plus 1 bt plus 1. And then I'm going to do triangle inequality where I introduce a. This is at most x bt plus 1. This is x is equal to xk. Right, so this is xk. Minus a bt plus 1 plus a bt plus 1 minus x bt plus 1. Okay. Now, what does the hard thresholding operator do, right? What is this guy? This guy is just the hard thresholding operator applied to this, right? Applied to A. So what does the hard thresholding operator do? It gives you the best k-sparse approximation to the vector. It takes the largest k entries in magnitude, right? So this norm is definitely at most this norm, because that is the best approximation. So this is at most 2 times x bt plus 1 minus a bt plus 1. Right? And now what I'm going to do is just expand the definition of a. This is equal to x bt plus 1 minus x t bt plus 1. And then there's a minus pi transpose y minus xt, pi, I forgot that pi again, pi xt bt plus 1. I should really, this is restricted to okay. So now x minus xt is just the tth residual. And now what is y? Y is pi x plus e. So I have pi x minus pi xt. That's also pi times the residual. So using our notation, we can rewrite this. This is equal to 2 times the residual, the tth residual, times b t plus 1 minus pi transpose pi, our residual bt plus 1. Minus pi transpose E actually in here. Okay. And now what I'm going to do is I'm going to write R as being RBT plus 1 plus RBT minus BT plus 1. And I'm going to do that. I'm going to do that to this R right here. So this is equal to 2 times RT BT plus 1 minus pi transpose pi R BT plus 1 BT plus 1 and then this is also B and minus pi transpose BT minus BT plus 1 pi R BT minus BT plus 1. Sorry, this is a little bit of writing nightmare. Okay, good. And now what I can say is, look, here I have identity minus pi transpose pi applied to this vector. And then here I have, so now I'm going to do triangle inequality. This is at most 2 times the operator norm of the identity minus pi BT plus 1 transpose pi BT plus 1 times the norm of R. This is all RT. Times the norm of RT. Plus 2 times the operator norm of pi BT plus 1 transpose pi BT minus BT plus 1 times the operator times the norm of this thing, plus okay. So now remember that pi has 3k RIP. Okay. In particular, it has. So B is a particular support, right? This has k elements in it. This has k elements in it. So B has size at most 2k. So because we have 3k RIP, that's even k more than we need. This thing is at most epsilon. So here we have 2 epsilon times the norm of the tth residual. Remember, we're trying to bound the norm of the t plus first residual, right? This is RT plus 1. So we're saying that the norm of the t plus first residual is at most something in terms of the tth residual, which is the kind of thing we want to see. So this thing here is at most 2 epsilon times the norm of the tth residual plus, again, this is the kind of thing we've seen before, right? If you look at disjoint columns of pi, then if you look at pi transpose pi, where each one of those instances of pi is disjoint columns, then the operator norm is O of epsilon. That's again what we saw just now when we're analyzing Krahmer-Ward. Now, what's the total size of all these sets? The total size of all these sets is this has size 2k. And then BT brings us an additional at most k. So in total, these union of these sets has at most 3k. That's why we need the 3k RIP. So again, we have another 2 epsilon times RT plus this guy over here, which is plus the norm of E. 2 times basically square root of 1 plus epsilon times the norm of E. This 2 is that 2. Also, we preserve squared norms up to 1 plus epsilon, so the non-squared norm is up to the square root of that. So this is equal to 4 epsilon times RT plus 2 square root 1 plus epsilon E. Okay. Oh, and I should say, this is, okay, I screwed this up a little bit. This is actually BT. BT plus 1. And this is actually BT minus BT plus 1. Right? So really, this is actually BT plus 1. And this is actually BT minus BT plus 1. So what I can say is 2 epsilon RBT RT BT plus 1 plus RT BT minus BT plus 1 plus this 2 square root 1 plus epsilon E. Okay. And these are norms here. But again, we have this. Let me wrap this up, basically out of time. We're like almost there, so I'll say one thing and then if there's anything missing, I'll just add it to the notes. So remember, we had this thing before where we said A plus B is at most, I think 2A plus B root 2 A plus B squared, or A, is that right? What do I want to say? No. Is that most 2A squared plus B squared? Something like that. Yeah, maybe I'm missing. Well, what I want to say is this. So what I want to say is that in general, if you have x plus y, and they have disjoint support, this is at most root 2 x plus y when they have disjoint support. Right? So if you just apply that to that, that thing is at most 2 root 2 epsilon times the norm of RT plus 2 root 1 plus epsilon times E. Right? And then this thing is less than a half for epsilon less than or equal to 1 over 4 root 2, which is why we got that. So then this thing will be at most something like 1/2 times the previous thing plus something like 3 times the number of E, if you plug in that for E, for epsilon. And now basically, now that you've established this, you can just use induction. Induction on T will imply that theorem. Okay. So remember, there's a less than twiddle here, meaning that there's a constant that's multiplying this whole thing. So if you choose that constant big enough, the induction will go through. Okay. So I'll leave it at that, and I'll fill in anything. I guess I discussed everything except for really, dealing with this E tilde, which is dealing with the norm of pi at the tail. But I'll put that in the notes. It's not much more than what we've already just seen.